Here to introduce Jacob, whom none of you know, but Jacob was invited to give a talk to a conference in China, and turned out to be a talk and a tutorial. And I figured if he's going to enlighten a bunch of people at the conference, he should enlighten us first about all the great things he's been doing to make training neural networks really fast. Are you going to talk about runtime as well? And have them evaluate really fast as well. So this is sort of the practice talk, I think, for or it's just like a mush of both the tutorial and the.
It's the keynote because I figured that people here are going to ask questions.
Okay, good. Yeah, so this is basically a dry run for the keynote at the conference. Thank you.
Hi. Yeah. So as Arul said, so there was a 3-hour tutorial and a hour keynote, but they're both very similar. The tutorial just has more stuff. So this one is basically the keynote, but it's I figured that people here are going to ask questions, so I think it should be appropriate amount of time. So the title is A Practical Guide to Neural Machine Translation, but the title is fairly misleading because this isn't really much about machine translation. It's more about GPUs and recurrent neural nets and understanding how GPUs work and how to make recurrent neural nets work fast on them for the first part, and then the second part is understanding how to make various tricks to make them faster on the CPU. So certainly, like there is, it's geared towards these type of sequence-to-sequence models for NLP, but there should be a wide array of things that it should be applicable for. So this talk is focusing on large-scale NMT systems, but other sort of large-scale RNNs, especially for text. And I'll talk about what's special about text compared to other stuff like speech and images. So how we brought the training time for a state-of-the-art NMT system down from 15 days to 3 days on a single GPU, and how we were able to achieve 100 words a second per CPU core on a state-of-the-art NMT system, which is comparable with our fastest SMT system. So, but first I'll just give a couple slides giving a history of neural machine translation. So Bengio in 2003 had this neural language model, which is very similar in terms of not just concept, but the actual design to how existing neural language models work. So you project the input n-gram into an embedding space for each word, and then you have a big output layer. And people have tried to use that for machine translation with mixed results. In 2014, I had this neural network joint model, which got a big gain by not just being a language model, but being a strong translation model. But this was still a additive improvement onto existing SMT systems. And then 2014, there was the Sutskever paper from Google where they did a sequence-to-sequence style model. So this is basically just running a RNN, either LSTM or GRU, over the source sentence, getting a hidden state, and then using that to run another RNN where you produce one word at a time on the target side. Of course, this has a problem that you're bottlenecking your entire translation as a fixed size vector. So then people started this attention model, which was introduced by the University of Montreal. And I'm not going to really go into the details because it's not really, I don't really talk about it very much, the actual details of the attention model. But the important part is that it's a different type of model that's not just a vanilla, GRU or LSTM. And so in this case, basically you can figure out exactly what part of the sentence you want to look at in a differentiable way. So I might add more for the talk that actually goes into machine translation. But the important part is that these are really painful to train. So, I mean, probably nothing compared to, not any worse than people who deal with speech recognition for a long time. But for the shallow models, and these are 4 different papers from 4 different groups that use 4 different toolkits, and they're all, top groups of state-of-the-art systems. And so we see 2 weeks, 3 weeks. These are both on 1 GPU, and then on Google's model used 6 days on 96 GPUs. Baidu's model is used 10 days on 32 GPUs. So it's really difficult to do research with such large turnaround times. And of course, also running a single model on 36 or 32 to 96 GPUs is very not feasible for many people, especially you know, educational institutions and stuff like that. So what we're trying to do is to significantly reduce that without just expanding to an insane number of GPUs. So what we're going to talk about in this talk is, first part is going to be training. So efficient implementations of RNNs on GPUs. So it's going to be how GPUs work. Then how we can fit large architectures onto a single GPU rather than having to split them onto multiple GPUs. How do you handle variable length sequences efficiently, which is a big problem for machine translation and many other tasks. And how do you deal with the large output vocabulary? Because for machine translation, you have like 100,000 words in your vocabulary, and you don't want to have to do a full softmax over that. So we're going to talk about how that can be reduced. And then how you deal with large weight sets in multi-GPU training. Because if you just do the standard approach of transferring all the gradients and all the weights, actually you'll end up bottlenecking yourself because you have such a large vocabulary size that you're transferring so many embedding weights and output weights at every time step. And then part two is inference, which is deployment or runtime. So various tricks that speed up the model by quite a bit, and also how to choose a model for optimal runtime performance. So this talk is very heavily engineering focused. It's not a high-level talk. I do assume basic knowledge about neural networks. I don't really have time to go into, because I assume that people who are going to be operating at this level generally are going to have fairly knowledge of neural networks and recurrent neural networks and stuff like that. And just some terminology that I'm going to use a lot. So GEM is just a matrix multiplication. And I use this a lot, but it's just like multiplying two matrices together. It just comes from the BLAST network. Operator, that is a layer in the network or some other operation in the network, so like a 10H or a sigmoid function. And it's also called a module or like a node or whatever, depending on what toolkit you use. And whenever I say optimization in this talk, I'm talking about program optimization, not numerical optimization. If I'm talking about numerical optimization, I'll say weight updates to make it clear, because I'm going to talk a lot more about program optimization, making things run faster and with less memory than numerical optimization. So, okay, we're going to get right into it. Okay, so there's been a lot of work. Why is this not updating? Okay, so there has been a lot of work on speeding up neural networks. A lot of it has been focused on convolutional neural networks for image recognition, which is, it's difficult for that it is very difficult to speed up convolutional neural networks, but it's a little bit different because you can kind of optimize one particular component and then use it for lots of different neural architectures. RNNs are much more model specific. Like if you want to make some tiny tweak to the model, you have to you can't use an existing optimized LSTM. If you want to use even a tiny modification to the LSTM, you kind of have to use the entire thing as a black box. And so that's why it's generally nobody's going to optimize their own CNN. They're just going to use some existing toolkit written by a GPU expert. But right now, there's no toolkits that optimize RNNs optimally. So as of right now, you kind of have to do a lot of stuff yourself. NLP tasks also have variable length sequences, which is a big difference, and that's a big pain to deal with. Usually for images and stuff, you just kind of have a single image or some fixed number of samples from a video or whatever. But for NLP, you're going to have sentences with an average length of 15 words, but all the way up to 100 words if you want to deal with long sentences. So that's a big issue. And they also have a very large number of parameters. So you might not have very many recurrent parameters, but you might have 100,000 word vocabulary, source vocabulary, plus target vocabulary. So you could either have 300 million parameters of a network that's not that big or deep, which means that you have 1.2 gigabytes because there's 4 bytes per float that you have to deal with. And so if you start dealing with multi-GPU transfers and stuff like that, it's quite painful. So background on recurrent neural networks. There's two popular variants, the gated recurrent unit and the LSTM. You also need the attentional version of one of these for MT and other tasks. So cuDNN already has an optimized implementation of these, as do other toolkits. Usually cuDNN is going to be the fastest one basically right now. It's basically as fast as it can be on the GPUs. But if you want to make even a small change, you can't do it. So if something like a large change, like an attentional RNN, it's totally hopeless. But generally, you can do about 5 times faster and 5 times less memory usage with an optimized RNN compared to a non-optimized one. Yeah, and you can't use it with any variant. So I'm going to talk about how to optimize a GRU just because it's fairly simple. Of course, you wouldn't actually ever optimize just this vanilla GRU because it's already been done, but it's important. It's just to show kind of the techniques that are involved in optimizing any type of RNN. So this is the GRU function. This is the visual representation on the right and the mathematical representation on the left. So xi is going to be the input at a particular time step. So this is the vector representation at a time step, but it could also be the scalar representation because these are all elementwise. And so, actually no, it's a vector representation, yeah. So xi would be like the word embedding of the previously emitted word, and hi is going to be the previous hidden state. So it's got these gates where you have the update gate where you say how much of what the mixture between my new candidate and my old hidden state is. So that lets you do lets you keep information over long time steps, and it's got the reset gate where you have say what's the mixture between my previous hidden state and my new input. And but the exact details, like the intuitive understanding, isn't really important. It's more, I'm going to go through the details of how this works. So in terms of, the key point is that it's a mixture of matrix vector multiplications and element-wise functions. So in this case, we have these 6 matrix vector multiplications and then a bunch of element-wise functions, 14 element-wise functions. And an element-wise function is basically anything that operates on each element of a vector or a tensor independently. So these are fairly easy to implement on the GPU. Another thing to note that we will, what's going on? That's kind of important is that this thing can also be written as, well, no, this isn't actually right. So yeah, it's not W, but it's a different weight vector. If you were to concatenate these weight vectors and concatenate, doing the matrix vector multiplication of two independent matrix and vectors is the same as concatenating both of them with some certain transpose. But it's better to keep them separated for the purposes of these type of optimizations. So in general, you're going to want. Yeah, no, this is not right. Yeah, this is not right. It's not WU. It's a different vector. It's a different matrix.
No, but even if it's different matrix, that would have many zeros, right? No. Because if X and H have different dimensions, then how can you concatenate them?
It's
you don't have the same dimensionality between input.
Yeah.
One appended to the other.
Oh, you appended. I see.
Yeah.
Okay. It's a vector.
Yeah. So in terms of how we actually implement these on the GPU, so it's written like this, where y equals w times x, where w is a weight matrix and x is an input vector and y is the output vector. But on the GPU, there's different ways to implement it, but the way that I implement it for convention, and well, not just for convention, the way I literally implement it, but there's different, there's equivalent ways to do it. But this one is x times w transpose. So x is actually a matrix of different samples where, because mathematically, the neural net applies on one sample at a time, but if you're running on the GPU, you want to do a lot of samples at once and mini-batch it in order to be efficient. So x is an n by n matrix, where n is the mini-batch size, and then w transpose is an n by p matrix, and then y is an n by p matrix. And so, yeah, I'll explain why having w be transposed is important in a second. But in general, optimizing matrix multiplication is very hard, but you don't actually need to do that yourself. You just call out to cuBLAS sgem in the cuBLAS library, and that will do the matrix multiplication. But what is important is to understand, which I'll get to in a second, like how it works in the GPU and kind of have an intuition and I'll show some graph to kind of show like the speed for various dimensions, which is like the most important thing to know. And then on the GPU, the elementwise functions are just implemented as CUDA kernels. And what that means is that, like on the CPU, you would have, for something simple like add two vectors elementwise, you would just loop over it and say add them. On the GPU, you just write a kernel that just adds a single element, and then this is kind of does the implicit looping. It runs a bunch of things independently on different CUDA kernels, or it runs the same kernel on different CUDA cores. And so you just write a single element, and but it's basically the same code as the CPU. So it's fairly simple to write a single element-wise kernel. And so these specs are mostly just to kind of understand the GPU. So you'll see where this is going in a second. But so GPUs can get 7,000 gigaflops a second. So this particular GPU, which is almost state of the art, it's one generation behind the one that just came out. But it gets 7,000 gigaflops a second in terms of floating point performance. That's the peak one that it can do. But it only gets around 300 gigabytes a second of memory bandwidth, which is still really good. Like CPUs only get about 100 gigabytes a second. It's got these lots of parallel cores. So there's 2 points when you're thinking about GPU computing. The one that you kind of hear a lot is that you want to make sure that all your CUDA cores are always busy, right? So you have 3,000 cores. If you only write a CPU code which just does regular loops and stuff, and you only use one of those cores, you're only going to get 0.03% of peak performance because you're only going to be using one out of the cores. But the other thing which is equally important and more important for our purposes, which is that you want to read from GPU RAM as little as possible. So if you read a float and only use it once, then you're reading in 4 bytes, which you can only read at 288 gigabytes a second. And so that means you can only get 72 gigaflops peak, even though the theoretical max is 7,000. So you're only getting 0.1 utilization if you're just reading from GPU RAM. And this is super important. And GPUs have local memory and shared memory. So they basically have their own concept of L1 and L3 cache on a CPU. But it's even more important on the GPU than on the CPU in some ways. So this is showing how matrix multiplication kind of works on the GPU. So this is the batch size. So this is if we have an n by m matrix. So this is the first dimension n, right? And even if you go up, and then these are varying sizes of m and p. So this would be the equivalent of a matrix if you had like a 500-dimensional fully connected layer, and this would be a 1,000-dimensional fully connected layer. And then this is 1024 by 3092. Where the importance of that is that something I'll get to a little bit later. But there's 3 matrices that are involved in the GPU in the GRU multiplication. So this is showing basically the bigger these dimensions are, the more efficiency you get. So you get terrible efficiency all the way up to around here. And for the smaller matrices, you don't get peak efficiency until you have a mini batch of 1024. And so, of course, the larger the matrix is, the better the efficiency is you get for smaller mini batches because you can saturate all your cores and make better use of the RAM because you can reuse things more and more. So one question is why we can't just use a large batch size like 1024 if that's what saturates the GPU. So the problem is that on the for RNNs, you have the mini batch is actually a collection of sequences because every time step depends on the previous time step. So if you have these 3 sentences, you mini batch them together. And so it's actually a mini batch size of 3, really, because you can't compute this one until this one is done. So you have to kind of make this matrix or tensor if these are embedding vectors. So you can think of this as a 3-dimensional tensor where this is your mini batch dimension. And then this is your vector for the word embedding, and then this is the time step. And so if you had 50 words and 1024 sentences would actually be 50,000 words, which won't fit into memory, and it's going to cause training inefficiencies. So you can't just use a large mini batch like you could for other tasks with feed-forward networks. So in terms of optimizing the GPU, given what we've seen so far, there are 2 tricks. So one of them is gem fusion, which is combining all matrix multiplications into a single call. And I'll go more into detail into both of these. And then the second one is elementwise fusion. So when you have 2 elementwise functions applied in sequence, you just combine them into a single kernel. So both of these have the same goal, because both of these will parallelize to all the cores fairly well. But the goal of both of these is to minimize the amount of reads and writes to GPU RAM. So GemFusion, we can see is, so this is just the same GRU formula we saw before. I just wrote it again so we can figure out what to do. So we see that we take Wxi and we multiply it by the same xi gets multiplied by Wu, Wr, Wc. And so because of that, it is, it's using the same vector 3 times. And so you can concatenate those 3 weight vectors and then multiply by xi, and you get a concatenated version of the weight matrices. So this is pretty typical. Most toolkits have an optimized version of the LSTM or whatever that does this. I don't think any of them can do this automatically because it kind of breaks certain assumptions. But visually, you see that you just have, so these are all assuming row major matrices. So this is all contiguous memory as we go down the rows. And so normally this is why we transpose the matrix, because then you can just concatenate the 3 matrices in memory, and once you transpose them, then it all just works out. You don't have to actually, the weights are still contiguous within their own logical representation. So WU is still a set of memory that's one contiguous unit. You'll notice that this Y is not contiguous, or that YU is not contiguous. It's actually interleaved between the 3 matrices. And so that's something that we are going to have to deal with, which you can either do by explicitly slicing, or you can be more efficient and actually write a fused kernel which is aware of this layout and actually uses this layout naturally without having to do any explicit writing. But the weights are still contiguous, which is nice because that means that then you can, if you want to have like a different update function for the different weights, then you don't have to rewrite them every time. And the reason why this, we can see from this previous slide that the flops you get from doing a 1024 is significantly better than what you get from doing the 3092. So the fused one is this top guy, and then the non-fused one is this guy down here. So it's basically seeing that. Yeah.
You could just refer to colors.
Yeah. The top one, the dark blue one is the fused one, and then the green one is the non-fused one. So you still, if you use a very large mini batch, you still get the same thing at the end. But for a reasonable sized mini batch of like 128, which is what we typically use, there's a huge difference. There's over twice the difference. So it's really crucial to do this trick. Then there's another type of gem fusion, which is that you can fuse across time steps. So we saw here that this is for one time step. So HI depends on HI minus 1. And so you can't compute HI until you've computed the previous one. But for the product of WU times XI and all the W's times X, you know all the X's ahead of time. At least if you architect your toolkit in a certain way, you don't know all the X's ahead of time. And so you can fuse all of them across time steps also, which basically means, and if you if you lay out the memory in a certain way, you actually get this for free, meaning you don't have to do any sort of rewrites. Because if you just encode X as a 3-dimensional tensor, where it's time step, it goes over time steps, and then over mini batch examples, and then over dimensions of the vector, then you get then you get this layout naturally. And so you don't actually have to rewrite anything. You just multiply this vector by the same fused weight matrix, and you get this big 3-dimensional tensor as your output. But it's all contiguous. So you can just interpret, you can just interpret this chunk as well, it's not, this chunk is just one contiguous chunk of memory. So you can just treat these all as separate chunks of memory down the line. You don't have to do any sort of rewriting. And the advantage of this is, of course, if we go back to this guy, that if we have a sequence length of 20, and we have a mini batch size of 64, then we've basically gotten like all the way up to here. And so we're going to be getting peak flops rather than down here. This is like, we're getting 3 times efficiency in that case. Of course, this depends on your mini batch size and everything else like that. But in general, you're going to be getting a much better efficiency by doing this for that part of the computation. So in terms of, we can see here the flops that for these various things. So this would show, this is if we have a 500-dimensional GRU. If we don't do any fusion, we get about 1150 gigaflops. If we just use the weights, which is the last slide, we get 2500. And if we fuse the weights and the time steps, which is this slide, we get 5500. And then, of course, the bigger the dimension of the GRU, the better efficiency you get in the baseline. So if you have a larger dimensional RNN, then you get less efficiency speed up. But you still get, because this is about the peak that you can get on it. Like 7,000 is the theoretical peak, but this is the real peak that you can get for matrix multiplication. And so you get about peak either way. But you don't have to have insanely large dimensions to do it. Because of course, this is much slower than this one, even though the number of flops is the same. And so elementwise fusion. So it has these 14 elementwise functions. Toolkits, generally, the way that they work is that somebody handwrites each one of these functions. So somebody handwrites an elementwise add. They have the forward pass, which is shown here. Then they have the backwards pass, which is not shown here. And then once you have these handwritten things, you can just use the chain rule to chain them together automatically pretty easily. So you don't have, it's nothing. You don't have to do any like real derivations or anything like that. It's just pretty typical taking a graph and doing it. The problem is if you do like an elementwise function like this, it's doing 2 reads and 1 write for every element, which means that given all the things I showed before, that we can read at 300 gigs a second, but we're reading 12 bytes, which means we're getting 24 gigaflops. And that means that we're getting, out of our 7,000 possible total gigaflops, we're only getting 0.03% utilization. And so even though we're doing a lot fewer element-wise operations than matrix operations, this will still create a big bottleneck if you don't optimize it also. Because it's so inefficient to do if you were to really just do this the way that basically every toolkit does it nowadays. There are some ones that are trying to do it automatically that I've seen recently, but right now there's no toolkits that are doing proper element-wise fusion, and so you get terrible performance. So the solution, which is either automatic or manual, is to write a single kernel which uses all the element-wise operations, which would be run in sequence, meaning run without any non-element-wise operations between them. And then you do the same thing for the backwards pass. And then the other benefit of this is you get a huge memory saving just for free, because normally a toolkit will save the output of every operation because it doesn't know whether or not it's going to need it for the backwards pass or not. And in general, it has to assume that it will need it for the backwards pass. In this case, either manually or automatically, you just take the inputs of the matrix multiplications, and take the output of the fused kernel, and you basically saved 4x memory for free. Because anything that you need to compute in the backwards pass, you know that you have to recompute it in the kernel anyways, and it's cheap because doing actual operations inside of a kernel is 7,000 gigaflops. So you can do tons of stuff for basically free. It's all about the reads. So an example. So this is just a. This is just a literal kind of. It might look actually doesn't look that complicated, I guess, but it's just a literal like writing of the GRU. So these all assume. So these are the output of matrix multiplications, right? So we assume that we've already done done these matrix multiplications, and now all we do is we get our update gate. We just sum them, take the sigmoid. This should be reset gate. Sum them, take the sigmoid. Sum them, take the 10H. Apply the reset times this guy. So it's literally just writing down the exact equation from the matrix multiplications and not storing any of the intermediate values, and then computing the final output, because all this stuff can just be done at once. And then for the backwards pass, it's a little bit trickier. Ideally, the toolkit would do it for you automatically. In my case, I just did it manually. It's a little bit painful, but hopefully soon it'll be done automatically. So here are the end-to-end optimizations for a GRU. So, and this is on a Titan X. And so we can see that, so these three columns are, 64 mini batch, 512 recurrent, 128 mini batch, 512 recurrent, 128 mini batch, 1024 recurrent. So this is going from smaller to bigger. Of course, and this is not, remember, this is not speed, this is gigaflops. So this one's going to be a lot, probably going to be, actually it's not even that much faster, but it might be faster than this one because you're doing less computation. But in terms of efficiency on the GPU, you're not getting very much efficiency. So, yeah.
This is now end-to-end, right?
Yeah.
Okay.
There's other forward paths, but yeah, the back.
But everything.
Yeah. So when you have a small one, even when you do all these tricks, you can't ever really get super good efficiency because you're going to end up bottlenecking. It's basically Amdahl's law. Like you can get the one part of it be really fast, but then the other part, like the regular matrix multiplications of the recurrent layers, will kind of bottleneck you. So typically,
I want to compare that with the earlier curve you draw. It looks like from 512 to 1024, it didn't double in the previous curve. Maybe I missed something.
The previous curve was just the matrix multiplier.
Oh, okay, so without fusion. Right. Okay.
That one was it. Sorry, Jacob.
yeah.
So this is almost more than double to go from 512 to 1024, whereas in the previous curve, it was only about maybe 20% higher.
Is that
The
true?
difference is the fusion versus, that curve. So 512 to 1024 was not really as much gain. The difference is because fusion versus not fusion? Or?
No, it's about.
No, 512. Right?
This is about. No, this is. It's not quite double, but it's. There's a pretty.
512 to 1024. Right, look at that.
Yeah.
To the right.
No, you're talking about mini batch size. This is recurrent size. So this
I
is
see, okay.
so the right comparison is between here and here. For this is 128 mini batch. So it's not quite double, but it's.
But this one doesn't have the fusion, right? The difference is the fusion with no fusion, or
Yeah. So well.
like here is
That was just a basic matrix product, right? Fusion is something you do on top.
on top of it. So that
The first two fusions are moving
I see.
the point
Okay,
in the
okay,
curve,
okay, okay.
moving
So-
to different places.
okay, good. So okay, good.
Yeah.
So M, I'm confused. Yeah.
Yeah. So this is the end
So
to end.
M is the recurrent size rather than. Okay.
Yeah. So M. Yeah. N is the maybe I mixed it up, but N is the batch size and M is the recurrent size.
The other way around.
Okay. Yeah, and then but basically in all these cases we can see about 4x speed up or so by doing these three things. And it's important that you kind of have this bottleneck effect where if you only were to do this without this, you would see a much worse than this because like you end up being bottlenecked by the slowest part of your computation. So to get good performance, you really need to do all of these things. Yeah, and of course we don't get. So this is the 128 by 1024 is the typical one that we do, and that is that's the one that gets near peak flops. And I also compared this. So this is my own implementation. Of course, I did all these ablations, but when I compare it to Cudi and N's implementation, it's very similar, to within 5% of the speed here. So, yeah.
So Cudian also does this trick that across multiple layers they use pipelining. Have you tried that as well?
I did. So it doesn't matter so much, like here, because I haven't actually implemented that myself. My impression is that it doesn't help unless they used like a mini batch size like 32 when they show those benchmarks. And I don't think that for large mini batches like 120, it's going to make any difference because you're going to be utilizing the GPU pretty efficiently anyways. Because like when I tried to use multiple, for like the basic implementation, I'm not getting into streams. Like there's another concept of CUDA streams where you can do computation in parallel. For the basic implementation, CUDA streams matter a lot. Like you get 2x efficiency. If you do it on the optimized implementations, like you basically get nothing from streams, even when you run multiple layers at once. So that makes me think that basically it's being, it's clearly not peak flops, but it's still utilizing the GPU. It's usually utilizing all the cores. So there's not a lot you can do. Okay, so those are basically the main tricks for optimizing. Yeah, just optimizing an RNN on the GPU. So do people have questions about this or? Okay, so the next problem is variable length sequences, which is not unique to MT, but it's certainly a big problem in all NLP tasks and also like speech and stuff. And so there's kind of three possible ways to deal with it. One is to pad all your sequences to the maximum length, which is very inefficient. Another one is to terminate the recurrent loop early. So it's tricky to do this with complex architectures because it kind of makes everything non-square, and unless you like pad it to the longest length. And so when you have something like sequence-to-sequence with attention, where you have one source length, one target length, and you have this kind of n-squared operation where you refer back to the source of the target, it becomes very, very problematic. So the third approach, which is what we use here, is to use buckets, which means that you just create different network graphs which share all their weights, but each network graph has different maximum sequence lengths. So this one, let me see if I remember to, yeah, so I have more information on this in the next one. But basically, the advantages of this are that everything is square, and another advantage I'll talk about in a second, but the idea is that, so you have one length, you have one bucket, which is just maximum length of 10, another bucket, which is maximum length of 20, then up 30, whatever. So you might have 5 buckets, each one's multiple of 10. And effectively, these are all just independent neural networks that happen to have the same parameters. But by convention, you instantiate them so that they are actually identical except for their length and their mini-batch size. Yeah?
So at this point, I need to point out the variant number 1, you can make this much more efficient by concatenating multiple sequences. So you don't actually pad the sequence all the way to the end, but if you have space there, you can fit another sequence, you would put it there, and that gives you much better efficiency. So that's what CNTK does.
I know, but it's very tricky to do that for complicated architectures. Like once you do something like attention and stuff like that, then having to do attention over part of a sequence which is padded into another sequence is quite tricky. But there's another big advantage of bucketing, which I haven't seen mentioned in papers. Abdul Mahad actually pointed this out to me. I didn't think about it, which is that different buckets could have multiple batch sizes. And so this has two huge advantages. So the first one, basically every publication I've seen uses a fixed number of sentences. So we use 128 sentences. But there's two problems with this. One is that the total gradient magnitude is proportional to the number of target words, because that's how many loss functions you have. And so what you really want to have is a fixed number of words, not sentences. So you want to say something like, we have 4,000 words. And so that means the different buckets will have different number of sentences. So for your really long buckets, you might only have 64 sentences. For your short buckets, you might have many more sentences. And so not only does it get you much healthier training because every mini batch has basically similar gradient magnitudes, it also means that, it's more stable because everything has similar gradient magnitudes. You can train with much longer sentences because you use a smaller batch size. But it's also much faster because the majority of the sentences are going to be fairly short, like average length of 15. And so for that, you can use a really large effective sentence mini batch, because if you're 4,000 words and your average sentence length is 15, then your mini batch size is like 350 or something like that, rounded to the nearest 64. And so if we looked at like that back at that curve, then 300 plus gives you much better efficiency even for smaller networks than 100. Yeah.
So a stupid question, is the traditional approach to just pick one bucket size per mini batch and the next mini batch has a different bucket size, or do people mix multiple buckets inside the same mini batch?
Because
that would address this also to some degree, right? Even if you keep the number of sequences inside each bucket the same.
Well, no, it's you want to have one mini batch it's just picked from one bucket.
Okay.
And there's an important reason for that, which is that you want to be able to. So I took out all the stuff with memory for time because this is the shorter version of the talk. But the really crucial thing is that you don't like you're instantiating basically 5 completely different networks that just happen to have the same architecture and share their weights. But because of they have not only different length, they also have different mini-batch sizes. They all basically have to be instantiated completely independently of one another. But you want to make sure that they share all the memory that they can. Because if you make the constraint that you're only ever going to run one mini-batch at a time on one GPU, then if you reallocate the memory, basically using virtual allocators, which is how I do it. So operators don't explicitly allocate GPU memory ever. They just use a virtual allocator, which says, I need this much GPU memory. During initialization time, they create virtual variables and say, I need this much memory associated with this virtual variable. And you can do this for every one of your buckets and also every one of your operators. And then you can have your graph optimizer, which fairly simple one that just says which things could be used at the same time and can then optimally allocate and reuse memory. And so what this means is that you can use much larger neural networks and use tons of buckets without any overhead. So basically, we actually use 150 buckets in our training because we don't do any padding on the source because we found it to be problematic to use. So we actually have, for every source length, we actually have 2 buckets. And because there's basically 0 overhead to buckets, we can do this, which has the other advantage that we're not wasting anything with padding. Like in most of these other papers, they waste around 30% of their time just by padding out to the next bucket, because like if you have a bucket length of 25 and your average length is 17, then you're going to be padding out an extra 8 tokens every single time. And yeah, so this way we only waste like 3% with padding, and we have it's very, because we have large data sets, we can afford to have so many buckets.
So if you already sort the length of the sentences, then padding overhead is very small, right?
If you only have if you only have 5 buckets, which is pretty, like a TensorFlow default implementation has 5 buckets, then if your buckets go from 1 to 15, 15 to 25, then 25 to 30 or whatever, then like the 15 to 25, it'll be the average waste might be 25, 30%, right? Because if the average length is like 18, 19 words, then it's going to be padded out to 25. So it doesn't, even if it's sorted, it's still going to waste, amortize, the amount is going to be the same, right?
Yeah, so the problem with this is that when you sum all these sentences with the similar length together, you lose the possibility of some of the recent NLP people's discussion about how to use this course information, the relationship between one sentence to another. And you totally lose that opportunity because the sentence really are connected to each other. Like Chris Dyer's work last year, you touched.
Yeah, I think there's ways around that. Like you can, in that case, you probably would have to do padding in terms of, it depends on how you represent. Like you represent the previous discourse as you're not gonna run in all likelihood as complicated a network on the discourse stuff as on the regular stuff. So you might run a shallower network or a smaller network on the discourse context. And in that case, you might just end up padding all your discourse because it's cheaper anyways. But yeah.
Sorry, one more question.
Yeah.
So do you have experience on whether sorting by length will actually harm your convergence? If you maybe start training on short utterances and later on go to long ones, but you don't really randomize anymore, right? You don't randomize.
It's still randomized per. It's only per mini batch. It's not randomized.
Right, so my question is that important in your experience?
I don't think so. I didn't try. It's certainly not sensitive. Well, it is sensitive to batch size in the sense that you can't make the batches, and you can't make them. They have a limit of how long they can be, but it doesn't seem to be that sensitive to batch size, which makes you think it's not sensitive to.
If you start with short sentences and you end with the long ones, is that better than randomizing the bucket lengths across many batches? Is that notably better or worse? Is that notably worse?
Are you talking about if you use curriculum training? Is that?
So let's say if you sort everything by length and you walk your way through the data in that way. So at first you update your models with all sorts of short sentences.
That probably would be worse. But I don't think it would be. I don't think it's worth to do it where each mini batch is the same length compared to if you were to do the inefficient thing and have each mini batch be random sentences.
Right.
Because I think that's.
So you're not doing this. The sorting, you're not doing it in this
right.
short log order. You're just doing that
batch.
for dividing up into batches, and then you pick a random mini batch to actually process.
Yeah, I mean, people have gotten good results where they just have completely different, where they have, 128 sentences of length 50 and then 128 sentences of length 10, and that seems to be a much bigger issue. Like what I saw, because in my old toolkit I was doing it that way, what I saw with this thing is that you can use a much larger learning rate because you get a much more stable training since everything has the same grading. Otherwise you have to kind of clip it to deal with the longest sentences, which is a problem.
Did you also find some issue with like variable amount of padding actually causing some weird bugs?
Well, you have to pad consistently with training and test time because the system can use the padding to cheat. So if you have different padding, like if you have different target length depending on, like for a single sequence it doesn't matter. If you have two different sequence lengths where you have the target length and the source length and you have different values, then the system can actually learn that the source padding is a deterministic predictor of the target length.
But at runtime you don't know how much padding. I mean you don't know the target length.
That's why I don't do any source padding. Target padding doesn't matter because that all just gets grading to 0. So the target padding is completely, it literally makes 0 difference. The source padding actually those tokens actually get integrated into the RNN, and so it can use those to, if you do it if you design your buckets in a certain way, if you make sure that there's no, yeah.
Isn't that a fatal flaw with source padding? Like in the
No,
sense
it only matters. It only matters.
know what the target length is going to be.
No, it only matters in a certain. It only matters if you have multiple targets of a different source or something. Yeah, I mean, if you only have a small number of buckets that are pretty coarse, it actually doesn't matter because there is no, like, the maximum length, like, is going to never. You're never going to reach below the minimum length on the target anyways. It would only do it in degenerate sentences. In the case where you have a lot of buckets, it does become a problem. But like, if you only have like 5 buckets, you never want to produce if something is length, 25 on the source, and then the padding tells it deterministically it has to be at least length 15 on the target. That's not really doing much because of course it has to be length 15. Yeah.
So are you saying the padding tokens are actually learned? They're part of the data that's fed into the network? That seems like a dumb idea. Sorry.
Well,
you can just short circuit them, right? You should just hop over them. You should just propagate through without doing anything forward and backward.
Yeah, but I would have had to write a new LSTM and GRU because you can't just, if you want to use the CUDA implementation, you can't do that. You have to add a special, because you can zero them out, but then they'll still have to basically make them completely unknown. Like you have to write your own implementation, which I didn't feel like doing.
Okay, I see. Yeah.
Okay, so yeah, so this is the CUDA GRU speed, and so this is I forget why I'm showing this, but it's basically just to show that the bigger the batch size is, the more efficient it is. So like if most of your sentences are length 15 and we can go to a batch size of 4,000 words, that means we can be right about here and be getting near peak efficiency. Whereas most other people are using somewhere between 64 and 128 and they're getting around here, which is much less efficiency, especially for the smaller network. Because we use this size on the source and this size on the target, so we actually use both of these.
Sorry.
Yeah. Yeah.
So when you compute the gradient, normally you take an average over the number of tokens or the batch size. What is the batch size that you use for that? Is that a constant number or is that different for each bucket?
It's technically different. It's the number of actual words, but it's going to be around a constant. But it's
the number of words, but it's roughly the same because you target. Okay, got it. Oh, this is.
But you use the actual number of words in each. You don't use a constant.
Yeah. Okay, so the next problem is large app vocabularies. So you have, a typical vocabulary size is around 100,000. A typical target hidden layer size is 1024. So that means if you were to do a full softmax, it's not the softmax that's the problem. It's getting the load just before the softmax, which means you have to do a 1024 by mini batch by 100,000 matrix multiplication. So that's terrible, and it would completely slow down the entire system. So what we can do is to subsample the output layer so we don't have to compute the softmax every time. And there's lots of different flavors. There's noise contrastive estimation, which is popular, importance sampling, blackout, which is another type of importance sampling, hierarchical softmax. So this thing, people have shown it to work okay for perplexity, but there was a paper by Google which actually, on a very large scale network, compared it to importance sampling and showed that it worked worse. This guy, I don't think I talked about this, but this guy, it's somewhat popular, but it doesn't work on GPUs because every sample, it goes to a different path of the hierarchy. So you end up having to, like, you either have to do very inefficient stuff on the GPU because you can't do these big square matrices. So the right thing to do is importance sampling. And so I'm going to talk about a variance of importance sampling. So the softmax equation is you get these logit scores by multiplying your output layer by your final hidden layer. So xi is, in this case, it's the logit score. And you take the log of e to that normalized over your vocabulary. And so now we want to approximate z using a portion of vocabulary. So this is what the importance sampling does. It's just a question of how we do that. So our formulation is to include the top m most common words and n randomly sampled words in the vocabulary. So in our case, a typical one that we would use would be 8,000 rounded to the power of 2 for the most common words and 8,000 for the random words. And this, importantly, you share this across the mini batch because that's how you get the efficiency from the multiplication.
So you also have to compensate for the ones you don't sample, maybe multiply a vector, a factor.
Yeah,
do that.
The next slide. So and then of course you also must include all the target words in the mini batch because those also have to be there, and you want to do it as a single thing. So it's the union of these two things, the common words, and then all the words that are actually observed in this mini batch. Yeah.
So the target words of one sequence are now included in the set for the other sequences.
Yes. So the crucial detail is that to approximate the softmax, you take the m common words and you do the normal thing, and then you take the n rare words and you multiply their scores after exponentiating them by this factor of alpha, which is vocabulary size minus m over n. And so what this is this is the inverse sampling rate. I'm missing a line here, but this line is messed up. I'll fix it. But basically if you have 92,000, if you have 100,000 words, you always include 8,000 of them. So you have 92,000 remaining words. You sample 8,000 of them. That means that each word has been sampled 92,000 divided by 8,000 times. So that's like 15 times. And so you multiply by this factor of 15 because otherwise you will massively oversample these rare words at test time. Because when you see them in the training as positive examples, you always, of course, train on them as positives. If you see them, so that means that when you see, they have to be pushed down equal amount, because the way that when you take the derivative of a softmax, you're basically pushing up the one that you see proportional to its probability, and you're pushing down all the other guys proportional to 1 minus the probability. So when you do it this way, we want to push it down by 13 times as much. Otherwise, they'll be 13 times oversampled. And there's a slight approximation here, which is that all the words in your current mini batch should not be multiplied by alpha. So you actually should do it for all the words that are not the current word. But if you want to do this nice square multiplication, it's a better approximation just to say, if you do it for the actual word itself, because of course these are all done independently. We're just doing it as a batch for efficiency purposes. But mathematically, you actually should do it for all the other 3,999 words in the mini batch. But it's a better approximation just not to do it, because if you do it for the word itself, you're going to completely break the training, because you're going to be multiplying it by 13 in the denominator and nothing in the numerator. So
this detail was not in Benja's original paper.
Yeah.
No, it's not there. Huh?
But yeah, I think if you use a large vocabulary, it doesn't really matter. But I think that it definitely matters a lot for smaller. If you're using a smaller sampling size.
The 2008 paper talked a little about this, but not as much detail. I think the paper didn't really say.
Yeah. But this works well. So this is just a visual representation of this. So we have our common words. Yeah. So this is our entire vocabulary. Sample 8,000 common words. So these are all then all the words in the mini batch, which are shown here, and then a bunch of rare words. We take the union of them, and then all the rare words that are not in their mini batch get multiplied by alpha. And this is just our 16,000. And of course we don't, if you want to always have a fixed size of like 16,000 or whatever. So you don't actually sample 8,000. You sample 8,000 until you get up to the total of 16,000, because you want to subtract off the ones that are here.
But then the alpha is variable.
But it doesn't really matter, because most of them are going to be that's the thing with using the common words, is that most of the words in the mini batch are going to be in the common words. You're going to get 90% coverage for an 8,000 word vocabulary. So that's why that factor ends up not really mattering that much. So, so this is test log likelihood, test blue score, and training speed for full softmax 4,000. Well, this is actually 4190, the power of 2, and 8,000 for a particular Chinese English set. It doesn't really matter what the set is, but so you do a full softmax, you get 10,000 samples a second. This is like a fairly small model because I didn't want to run the full softmax on the large model. And then for this one, so this log loss likelihood is not a very big difference, but it's a pretty big blue gain, pretty big blue loss compared to what we would normally see. So this is something that actually really hurt us for a while, which is that I didn't measure this. I just was using this thing, and because typically like you see like 0.1 in log loss will be like less than 1/10 of a blue point, but we see 0.8 loss here for this small gain in log loss, and so just make sure to be very careful about the difference between log likelihood and actual end-to-end, word error rate or blue or whatever. Yeah.
So roughly, what kind of vocabulary size would demand you to do something like this?
However, I mean, it's linear. It depends. It depends on if you have a really deep network and only 10,000 vocabulary, like if you're doing speech or something, then it doesn't matter because it's. But if you have 100,000 word vocabulary, and like we can see here for this, this is not like a toy model. It's smaller than our production model, but it's still fairly large, and we get a 2x speed up. So yeah.
So for the full softmax, you can use NVIDIA's GEM implementation, whereas for the sampled one, you can't really, right?
No, you just pack it into a.
So you make a copy and then.
Yeah, and it's efficient because you're doing it only once per mini batch.
Yeah. Okay.
Because you share it across time steps also.
So this seems to indicate that like if you do 8,000 plus 8,000, you don't need the full softmax. But I thought you actually are interleaving full.
I am doing this because it's this is one language. It could be different for different languages. We don't really know what the deal is. Like if for this case we know it doesn't, you don't know, but I don't want to run this for so I'm just doing this. It's more safe because what I'm doing actually for our protection models is every kth mini batch, which k is like 10, I do a full softmax. And that doesn't slow down very much. The one issue there is that you do have to allocate memory for it, because here you don't actually have to allocate memory for the entire thing. You only have to allocate 16,000 storage spaces for every word in your mini batch. Whereas if you do the one every 10, you still have to allocate space for it. So it takes 3 gigs of memory on your 12 gig card, which is a lot.
So among all the 4 methods, you prefer this method most? The last one is of course not applicable.
What's the other ones?
There are others.
So these are both. So these are both variants of important sampling. I think this one is very close.
The first one.
So this one doesn't work as well. It gets worse perplexity and it's just a much weaker model. I mean, it has the advantage that kind of and this one just doesn't work on the GPU. Okay, so we're almost done with training. So so we trained on 2 to 4 GPUs using asynchronous SGD. I have a longer thing about this in the tutorial, but basically we don't use model parallelism, which means that we don't split up the single model into multiple GPUs because that breaks a lot of these optimizations I was talking about, because you like the time step fusion and stuff like that. You can't really do that unless you do it only parse of the time steps, but you get much better efficiency with doing the model on one GPU. Otherwise, you have to kind of specially design your model to not have bottlenecks. So what this means is that we just have a different mini batch that runs on parallel on different GPUs on the same machine, and then there's some master, which could be, in our case, it's one of the GPUs. It could also be the CPU, and the weights all update independently. So they don't synchronize with each other. They're constantly updating against the master, and sometimes there's some tiny chance that they'll overwrite each other, but we don't care about that. But the problem is that the gradients and weights must be transferred from the GPU to the master, so either the CPU or the other GPU. And for NLP tasks, there's a large number of embeddings and output weights. The key thing is that most of them aren't touched in any particular mini batch. So in any case, you have 100,000 words, but for the output layer, you're only sampling 16,000 of them. And for the input layer, you're sampling only maybe like 2,000 of them out of your 100,000. So we only want to transfer those gradients. But then there's another problem, which is that even though I've only touched these certain weights, since the last time I got the weights from the master, other workers might have updated different weights, right? And so if you have to transfer only your gradients, but then you have to get everything back every time, then you end up with only saving, you still end up with a bottleneck. So there's two different ways that you could do it. One is that you have the master keep track of the state of every single worker, but that's super complicated. The other way is that you say, okay, for my dense gradients, which is my RNN gradients, my common word embeddings, I'm going to transfer them back every time. So maybe that's 15% of all your weights. For your rare word embeddings, you only transfer them every k times. So that means that one every fourth mini batch, I'm gonna always send my sparse gradients, and so 3 out of 4 times I'm going to get back these 15% of weights, which are my important weights, my recurrent weights, my common weights, and then the other 1 out of 4 times I'm going to get back all the weights. So I'm going to be slightly out of sync, but I only have to transfer very few weights. And this is zero effect on any training that we've done. So for a factor of 4, we haven't tried like much larger factors. Yeah.
Do you know if any of the other toolkits have that trick?
I don't think so, because you have to kind of mark weights specially. You have to change the interface of how you define weights, and I don't think that they have that. And so what we see here is that if we were to transfer all the weights, so in the blue line, we don't get a very good speed up at all, going from 1 to 4 GPUs. If we do a sparse transfer, we get a much better speed up. It's still, of course, not linear. Other toolkits, show closer to linear, but remember, this is the super optimized everything. This is super optimized GRU, super optimized attention. So, of course, if that's optimized, then there's some amount of time that you have to spend transferring. There's no way to optimize that, and you don't get linear speed up. But you do get, by doing the sparse transfer in both directions, you get a much closer to linear than doing the dense transfer.
What is the actual speed up? So from 1 to 2 is like it looks like it's actually more than 2x.
No, it's like this is starting 10,000.
Okay.
Yeah,
so that's like 11,000 to 22,000. So it's pretty linear with sparse transfer, right?
Well, then we go from like 11, 12,000 to like, so it's like a 3x speed up here on 4 GPUs. Yeah. And so here are some actual benchmarks versus published work. So the first one is a shallow network. And so this is against a published paper, but where they talk about how exactly long it took to do everything. We've also downloaded TensorFlow, Theano, my own old toolkit, and benchmarked them. And we see similar speeds to this. So it's not just this publication. It's lots of benchmarks that we run ourselves show similar speedups. So this is a open training and test set. So this is the exact same data, very similar architecture to theirs. The data, they train on a little bit less data because they used a subset of data. That's why their score is a little bit lower. But it's a very similar architecture. It's a 1024 bidirectional source layer, 1024 target layer. And they also use only a 15,000 word vocabulary. So none of this speedup comes from the sampled softmax. It comes from all the other stuff. There's a slightly slower GPU, but we see about a 5x speedup, which is consistent with everything that we've seen with TensorFlow and Theano and my old toolkit. Is about 5x. And this is both on 1 GPU. So this took our training time on 1 GPU down to like a little bit over 3 days. This is a large model. It's 400 million words of training data. So yeah, so it's not. This is similar to our production size models. And then if we do it on 2 GPUs, we can get it in under 3 days. And so this is a deep model. So this is Google's new model that they just released a paper on. So it's 8 1024-dimensional source LSTM layers and 8 1024-dimensional target LSTM layers. They did a full softmax. In this case, I do a sampled 16K softmax. So it's about the same speed overall. The important thing is that the GPU utilization and the same blue score. So it's because the models are identical. But the important thing is that they were using 96 GPUs and we only had to use 4 because one thing is that TensorFlow is not very efficient with memory, and so they did 8-way model parallelism, which means that every model and then 12-way data parallelism. So every layer of these 8 layers was on a different GPU. So most of the time the GPUs were just sitting around doing nothing because they couldn't fit it. I mean, they did some amount of transfer, but it's still like you can see that in terms of per GPU utilization, it's terrible. Yeah. Okay, so that's done with training. On to inference. Okay, so there's a couple important differences between training and inference. Number one is training's on the GPU, inference is on the CPU. It could also be done on the FPGA or whatever. It could also be done on the GPU or ASIC, but we're going to talk about the CPU. So training uses large batches, inference uses small batches. In this case, we're going to assume that we're only using a single request at once. You could mini batch a small number of requests, but in the general case, for a low latency scenario, it's much easier to assume that you're just handling every request independently. At training time, the weights are changed every single mini batch. At inference time, they're fixed, which allows for a very important optimization. And training uses the reference, and inference uses the beam search. And the effect of this is that at training time, the source and target networks are equally expensive. At runtime, the target network is B times more expensive than the source network, where B is your beam size, because that's the hypothesis that you're decoding. I took out the part where I talk about beam search in this talk, but it's in my tutorial talk. But basically, you're considering between some hyperparameter B, which we set to like 6. It's usually between 2 and 8 possible candidates at every time step, which means that you're effectively decoding 6 sentences on the decoder network, but only 1 sentence in the encoder network for every actual sentence that you see. So that ends up being important in terms of model selection. So the first and most important thing, which everyone does, is to use a short-list softmax. So if you don't want to ever do 100,000 word vocabulary at test time. You don't want to do it at training time, but you certainly don't want to do it at test time. So we want to put it down to a few hundred words. For MT, this is super easy. You run this standard word alignment that's existed for 20 years. You get a lookup table, and you take the union of all of them for the current source sentence. So we have the source sentence El Hombre Alto. You get, this is your lookup table. You get all these possible translations. You union them all, and then now this is the thing you softmax over every time. So you don't know exactly when you're going to produce which word, but you just take the union of all of it. For non-MT, you can't use the exact same trick, but you can do a similar. You just train a model on for non-MT, the best way to do it is to take your existing source network and to keep that fixed, and then to train a classification model on top of that, which is a single softmax and a bag of word classifier. That way you only have to do a single softmax and it could be a much smaller dimensional softmax. But I'm not even really including this in one of the optimizations because that's pretty typical. So the second thing is that we need fast matrix multiplication on the CPU. So we care mostly about small batch sizes of 1 to 8, because 1 is, single sentence, and then 8's our maximum beam size. So there's these two very optimized floating point matrix multiplication implementations. MKL is very fast, and it's actually free now. And both of them use hand-coded assembly by CPU experts. But because they use floats, you can actually do much better, especially for small batches, with 16-bit operations. You can get about 2x performance. And 16 bits is way more than enough performance for inference time. You actually only need like 8 or fewer bits of information. I don't know of any open source implementations that have this full suite. Well, this is not for you guys. I mean, of course, you can use the one that we use. It's the same one that speech people use, actually. But this is a code snippet of how you do it, just a dot product, not a full matrix multiplication. With SSE, there's similar stuff for AVX. SSE is just the older Intel processors have SSE, which is doing 128 bits operations, which means you can do 16, or you can do 8 16-bit operations at once. AVX is 16 16-bit operations at once, so it's even more efficient. So this is really not, I'm not going to go through this. It's really just to understand, just a code snippet as a reference for people. But the important thing is this performance, which is, so this is so the dark blue line is MKL, which uses AVX, but floating point AVX. The light blue line is using SSE, which is only available on, which is what's available on older chips. And then the green line is AVX. So we can see this huge performance of about 2x, which is exactly what we expect from going from, 2 optimized implementations, one of which is on 16 bits, one which is on 32 bits, And yeah, and so you get a 2x speed up just like that. So you can also do gem fusion on the CPU. So the weight matrices can be fused, but it doesn't matter that much. What matters more is to fuse the input vectors, which means that on the source, this is only on the source. So on the source, you know all the time steps, you know the entire source sentence at once. So you don't. So the same way that you would do it on the GPU, where you have El Hombre Alto, you would fuse those into a single gem. You do the same thing on the CPU, and so this means that you have a larger batch size, as we can see here, that going from a batch size of 1 to a batch size of 8, gets us almost 2x improvement, actually more than that. So if we were only do it a single sentence, if we only do it one word at a time, which is how some implementations would do it, you're really hurting yourself by a lot. So similarly, we can do element-wise fusion on the CPU. It doesn't matter as much as it does on the GPU, but it's a similar thing. You just this is just the GRU with assuming you've done matrix multiplications. Now you have what you want to write a kernel, so you add them together. You do a lookup table. So yeah. So also on the CPU, it's better to use the lookup table than to use the actual 10H and sigmoid computed from the functions, because especially if this lookup table is fairly small. And you can also write an SSE version of this if you want to for a little bit more efficiency, but this is just the basic version, pretty straightforward. Okay, this is a really important optimization, which is that you want to pre-compute certain information after training is done. And in particular, if we see this is just the update gate, right? So it's WU times XI. So XI, for the first hidden layer on either source or target side, is a word embedding. And WU is a weight matrix. So we can pre-compute the value of this dot product, or not dot product, this matrix vector product for all words in our vocabulary. So
combine these two terms together in the previous slide. So what do you pre-compute in your earlier slide?
Well, fusing them just helps with caching. It doesn't really change the amount of computation. This is actually just pre-computing it. So this means that this term is actually just stored in a lookup table. And you can only do it for the first layer, which is why, so if you have multiple layers, you can't do this trick. So for the first layer, you want to do this trick. For the other layers, you want to do the fusion trick. This one is basically free, though. Once you've computed it. So, so this is just, you have 1,000 by 3, 1,000 vocabulary size. Each word is a row in it. You have your weight matrix. Multiply them together. Now you have something with the same number of rows, but you have your matrix vector product already computed. And you just store that in a lookup table. And so this halves the cost of the recurrent of the layer if the embedding size is equal to the recurrent size. But it only works on the first layer because it's the only time where you know what X is. This means that the first layer is half the cost of other layers, which is important when you're just deciding to select the model. It does increase the memory storage by a lot because you now have to store 3 times recurrent size instead of embedding size for every word. There's a couple of things you can do to mitigate that. One is that you can store these in quantized form, 16-bit or even 8-bit if you want to. And the other thing that we do is we only pre-compute for the most common words. So the top 10,000 words is going to get us 90% coverage. And so we only need to store 1/10 the amount of space, but we get 90% of the speed up. Another trick here, this one's a little bit complicated. Well, it's just because I didn't talk about attention. But you can do a similar trick for attention. I won't talk about it. It's too confusing. OK, and then this is the other trick, which is you can so for the recurrent layer, if you have 2 hypotheses, so you have this beam of hypotheses, right? So we might have a sentence El Hombre Alto. We might have the tall man, the tall guy, the large dude, the large man. But you can see that these, and we're trying to produce now the next word after this, right? So, but these guys, they are the same except for their last word. And what this means is that HI is actually identical for them, because that's this part, and then XI is just the last word. And which means that for these two hypotheses, these will both result in identical vectors. So you just merge them together, and then you only have to do you only have to do one computation, which actually has a non-trivial effect because for like a beam of 6, we see about 65% unique tokens, which means that we effectively only have to do a beam of 4 when we actually use a beam of 6. So that's like a fairly non-trivial speed up.
You do this for both encoder side and decoder side, or just do one side?
We only do it for the decoder side because for the encoder side we only use a beam of 1. We only use a single mini batch at a time, and so you'll never see this effect. Okay, so now the speedups. Okay, so this is the baseline, which already includes the shortlist and Intel MKL. And so this, if you don't use the shortlist, you get terrible speeds. It's not like it's not tractable. But so this is already a fairly strong baseline. It's at least as fast as any of the published results I've seen. It's so 34 words per second per CPU core on a not a new CPU, on an old CPU. And now here are all the speedups. So you go to 16 bits, you get about 2x right off the bat, which is what we showed before. You do the gem fusion on the source. It helps a little bit. I was actually surprised it didn't help more. I think it's because I guess the recurrent part is the bottleneck. Pre-compute the embeddings.
Gem fusion is doing all the words at the same time?
On the source side, yeah.
So this is not matrix it's not per time step. This is fusing all the time steps.
Yeah, it's both.
So it still doesn't help that.
Yeah.
Okay.
Yeah. And this is our production model. So it's actually three source layers, one target layer, and then it's an ensemble of two networks. And the pre-computing matters a lot because, of course, you're saving yourself a huge amount of computation. Pre-computing the intention, which I didn't talk about, helps more. It's a similar trick. It's just done at the start of the training. I started the sentence and then offline. The kernel fusion helps a lot because you're doing, even on the CPU, all these memory accesses are pretty slow compared to keeping them in cache and registers. And then this final trick that I talked about of deduplication gets us in a little bit more. So what we get at the end of the day is about a 4x speed up and actually a model that's close, well, not literally state of the art, but state of the art for non-super deep models, and is as fast as a phrasal decoder. So 100 plus words per second per CPU core. So when we're trying to figure out what models to actually use, there's a couple things that you want to keep in mind given all these optimizations we talked about. So one is that the target layer is much more expensive than the source layer because of the beam search. The first layer is half the cost of all the other layers because of the pre-computation trick. The cost of layers is quadratic. So like, a 1024 dimensional layer is 4 times the cost of a 512 because it's a 1024 by 1024 matrix instead of 512 by 512. And so it's not just twice the cost. And a GRU is cheaper than an LSTM because it's only got 4 instead of 3. Or it's only got 3 instead of 4. And model ensembling actually can be worthwhile, but it's got very diminishing returns. So now I'm going to, so these are results with 2 models. So this is a deep model. Well, it's not a deep model. This is a bigger model with kind of symmetric source and target. So this is a different number of layers. And this is so like really this is the Google model, and this is our model that we had before that. This is the Google's production model, which this is my reproduction of it. And then we should take that and then reduce it. This is what you get. And then this is our model, which uses a deeper source layer. I don't have all the ablation experiments, but the important thing to note is so in our case, it seems like using a little bit instead of using these have very similar number of it's actually you can actually get fast results and slightly better results by using slightly deeper, smaller source networks rather than larger, because a 1024 network is actually 4 times as expensive as a 512 network. So that means that 4 layers on the source of 512 is actually the same cost as a single 1024 layer, which is why the speeds are similar. And then, but it's got a better blue score. And so this guy on here is our production system. So it's this is a different data set, which is why the speed's a little bit different. But it gets us over 100 words a second goal, and we actually do ensemble in production because of this fact that the first layer is cheaper, and we get this nice little almost a point blue gain. We get a nice little. It seems better than to then so yeah. So here it doesn't actually make much of a difference. Like so this case we're doing an ensemble of two one-layer models. In this case, we're doing a single two-layer model. They actually get very similar blue scores and very similar speeds. In our case, it's a little bit, yeah. Man, it's probably actually better not to ensemble. I don't know. We have to do more ablation experiments.
Assume all the trick you talk about for speed up apply to LSTM as well.
Yeah, I implemented all the on the CPU. I mean, on the GPU, in all these cases I still use a GRU attentional layer, but I use an LSTM. And there's only one attentional layer out of the 8, so it's basically one GRU and 15 LSTMs.
So why is it that the first layer using GRU rather than using them all together?
Because
most of the result I've seen that they have similar results. That's
Well-
the same as you got.
Well, so I wanted to. This was my attempt to reproduce the Google results. So I wanted to use exactly the right, but I didn't want to re-implement an LSTM with attention because that would be a big pain for no reason. So yeah, it's actually unclear whether or not ensembling is better. It's definitely, it's not, you have to train 2 models, so it's actually not better in that respect. So we probably should try more experiments to figure out what the best solution is. But we do see that basically after 2 models, like you gain very little. So it's really not, like these 8 model ensembles are really just to get your extra half blue point for winning a bake-off. Yeah.
Maybe a stupid question. What does ensemble model mean in the context of beam search? Are you running it completely independently and both, or do you do this on a word token by word token basis?
Yeah, so it's a regular log linear feature. One of them is the master model. So you say, give me the top k candidate. So you have your beam, and so for each, you have another hyperparameter, which is like the number of candidates. So in our case, it's like 10. And so we have a beam size of 6, and let's say 10 candidates. So then we take one of the models arbitrarily, maybe the one that works better. That's the master model that gets us the top. You don't have to do it this way, but we get the top 60, next words. Then we score them with all the other models, and then we. Okay. But it basically has no, because when you're using these are pretty sharp distributions. So top 10 is more than enough to. And you have to compute all these scores anyways because you're doing a softmax, so you already have the scores for free. Yeah.
Yeah. So your main takeaways here is that on the source, going deeper and narrower was better. Same amount of computation, but better blue score.
Yeah, and it's still, I guess the jury's still out on ensembling. It depends on exactly your network architecture. Here it looks like it's actually not worthwhile because you have to train 2 models and you get almost nothing for it. Okay, yeah, so that's it.